So rational expressions. Rational, this is just a fancy math word for everybody's favorite thing, fractions. So we're going to learn how to deal with fractions that have letters in them. So remember, in fractions, we are not allowed to divide by 0, right? If we divide by 0, we say, so some number over 0, we say is undefined. So when we have rational expressions, what we'll need to do first is restrict our input values. So think about like the x's you can plug in. So those input values, so a name for that we'll get to eventually, it's called the domain. So we need to restrict our input values to avoid, again, division by 0. To avoid x values that make the denominator 0, to make the expression undefined. Okay, so let's do some examples. Find all x values for which the expression is undefined and write the domain. So here we go. So for the very first one, here's a rational expression, 4 divided by x minus 1. So find the x values, right, that make the expression undefined. So it's undefined if the denominator is 0. So we set the denominator equal to 0. And we solve for x. So we see that this expression, 4 over x minus 1, is undefined at x equals 1. So undefined at x equals 1. So then the domain, the x's you are allowed to use, are all x's that aren't 1, right? Any other number is fine. So one way we can write that is the set of all x's. And then we do this line like this. It's just called set builder notation, such that x is not equal to 1. So this is called set builder notation. Okay, well, let's do the next one. For what x values is this next expression, x plus 7 divided by 2x plus 5, where is that undefined? Again, it's only, right, our only issues are if the denominator equals 0. So we're going to find out what x values make that happen. So I'm solving that linear equation. Divide by the 2, get the x by itself. Right, so the only x we're not allowed to use is x equals negative 5 halves. So undefined, so this expression is undefined at x equals negative 5 halves. So how would we write that set in set builder notation? So the set of all x's such that x is not negative 5 halves. Okay, last one. So again, expression is undefined if the denominator equals 0. So I have a quadratic equation this time that I'm solving. So we solve that by factoring. So go ahead and factor that difference of squares. X plus 2 times x minus 2. So x equals negative 2, right, is one of the values it can't be, and x equals positive 2. So this expression is actually undefined for 2 values, so undefined at x equals plus or minus 2. So then the domain, the set we can use, is the set of all other numbers such that x is not plus or minus 2. You can write them both out separately too, that doesn't matter. Okay, so we want to identify like what x's are allowed or not allowed. And then one of the other kind of like building blocks is we want to be able to reduce, right? So just like with fractions, right, we would reduce a fraction. So let's just remember what that was like when it was just numbers. So I have 15/35. How would we reduce that fraction? And I know some of you are already slashing away, but I want you to think about it. Let me see if I have a slightly less dense pen to write that with. So think about how you were doing that. So what you see is, right, 5 goes into both 35 and 15. So usually what you do is, right, you cross off the 15 and you write a 3, right, the value that you get after you take 5 into 15. Take the 5 into 35 and it leaves behind a 7. So this reduces to 3/7. Now I want you to think about that. So that means that these two fractions are exactly the same value, same place on the number line, right? It's just a different way to write it. Now I'm going to take you back one little step, and I'm going to kind of show you the math that canceling the 5 was. So 15 over 35 is the same thing. So I'm going to write that common factor. So 15 is 5 times 3, and 35 is 5 times 7. And now everybody's multiplying and dividing here, so I'm going to kind of do a little fancy footwork, and I'm going to grab that 5 over 5 out front, and then there's your 3/7. It kind of feels like an odd step going that way, but if you were multiplying, remember fractions multiply across so we can get back. But don't go back, because 5 over 5, right, is the same thing as 1, and 1 times 3/7 is 3/7. Okay, so that's kind of like why we're able to do what some of us just do just automatically. Okay, I think I'm going to stick with the pencil. Hopefully you can see that okay. My pen was just a little bit big. So let's see, for rational expressions then, we need to cancel common factors. Factors is important. Factor, right, part of a multiplication. So before we can reduce, we need to factor. So here we go. I have 6x squared divided by 6x minus 12. So to start with, we would factor the denominator. So how am I going to factor 6x minus 12? Well, since it's just linear, right, the most we could do is look for a greatest common factor. So it looks like 6 goes into both 6x and 12. So when I factor out the 6, that'll leave behind an x for the first spot, minus 2 for the second spot. So now here's that 6 over 6, right? And it's 6 times x squared for the top and 6 times x minus 2 on the bottom. You can tell it's a factor if it's multiplying everything else that's on that level. So now those are the 6 over 6's that I can cancel. And I'm left with a reduced but equivalent form, x squared over x minus 2. Okay, let's do the next one. So this expression, x squared minus 4 divided by x squared minus 7x plus 10, those are both quadratic. So when I go to factor them, I'm going to use my factoring strategies, right? So binomial. It has to be one of our special patterns. So that's the difference of squares. So x plus 2 times x minus 2. And then on the denominator, x squared minus 7x plus 10. So again, we're looking for a pair of factors that will multiply to 10, and that's positive. So multiply to 10 and add to negative 7. So x minus 5 times x minus 2. So now that we have factored, we can look and see, is there a factor that's common to the numerator and the denominator that we can cancel? Right? And of course you see there's the factor of x minus 2 in the top and the bottom. So let's go ahead and cancel those. So x plus 2 divided by x minus 5. Now, here's a big thing. Well, a couple of big things. You ready? These two expressions, right, the x squared minus 4 and then the x plus 2, these two different fractions are exactly the same, have exactly the same value everywhere except this x equals 2, and don't worry about that until calculus. So we've just written this original expression in an equivalent but reduced form. Okay, It does not reduce any farther. So even though there's an x in the numerator and the denominator, neither of those x's is a factor, right? So they're part of a plus and a minus. So that means they're not a factor. It's not x times anything, it's x plus something. So it's a term, not a factor. Okay, last one here. So if you want to pause and try some factoring on your own, it might take me a couple of steps on this one. So on the numerator, I'm going to go ahead and factor out the common factor of 8. And leaves behind a squared minus 1. And in the denominator, there's a 4. I'll go ahead and factor that out. A minus 1. So the 8 and the 4, right, those are both factors, and they have a common factor of 4, so we can go ahead and cancel that. So now it's 2 times a squared minus 1 over a minus 1. It's very tempting, right? Those look very close, but this is an a squared minus 1 and that's an a minus 1. They're not the same. But a squared minus 1 will factor for us. Right? So the 2 still tags along. So there's my 2. Factor that a squared minus 1. Difference of squares. So all of those factoring strategies are coming into play here. A minus 1 for the top and the bottom, so we'll cancel those common factors. And we're left with 2 times the quantity a plus 1. When you cancel from the denominator, it just leaves behind a 1, so we don't have to write it. You want to be a little bit careful. If you cancel everything out of a numerator, you need to leave a 1 in the numerator. We're leaving a 1 in the denominator here too, but we don't write denominator 1s. We can leave those off. They're extra. Okay, last thing. And these are opposite factors. Sometimes they come up, sometimes they don't. But just as something to know, if you have a minus b, that is equal to the opposite of b minus a. So two binomials and you're subtracting. If you subtract in the opposite order, the result is off by a negative sign. So how that helps us is if we're simplifying and we have a minus b over b minus a. Don't worry, I'm going to do an example with a couple of numbers. So same values, but subtracting in a different order, that equals negative 1. You know what? Hold on real quick, just so that you know what this is about. So if we think about like 8 minus 5 versus 5 minus 8. So subtracting two numbers in the opposite order. Well, what's 8 minus 5? 3. What's 5 minus 8? Negative 3. So if you subtract in the opposite order, you get the same value, but negative. So 3 over negative 3 is the negative 1. Okay, so if you're doing that with a rational expression, how is that going to help us? Well, here we go. So I have 5 minus x on the top. I'm not going to do anything there. On the denominator, we'll go ahead and factor that difference of squares again. X plus 5, x minus 5. So now when I look at this expression to see if I have any common factors, it's like, oh, nobody's exactly the same. But like 5 minus x and x minus 5 are opposite factors. So I can cancel those if I leave behind negative 1. So this is equal to negative 1 over x plus 5. Negative signs with fractions can live in a couple of places. Typically, I put them with the numerator. They can be out front. They can be with the denominator. If you would want to write it with the denominator here, you would need parentheses around it because there's more than one term for the denominator, right? This is totally okay too. Okay, well there we go. Look for your common factors, factor, before you cancel.